So for this problem now, of course, we'll use the same techniques that we did earlier. The functions now, we are working with y is equals to root x for the first problem, x is equals to 1, x is equals to 4, and y is equals to 0. The density here is uniform, which just means it's going to cancel out eventually. So we can leave it out. So we get that. Let's see. First thing, of course, you want to picture your problem. How is it going to look like? So in creating the sketch, of course, let's have the equations, the boundaries. These are the parameters we're working with. So let's create that sketch. So first, the key one is y is equals to root x. You have to know the shape of that graph. Y is equals to root x, of course, it's going to curve this side. So let's say that is y is equals to x. Y is equals to root x. Next, x is equals to 1. So let's say x is equals to 1 is somewhere here. Next you have, so x is equals to 1 will be, let's draw that line as well. Let's give it, can maintain blue as well. So this is x is equals to 1. Next we have x is equals to 4. X is equals to 4, let's position it somewhere here. So that is x is equals to 4. And lastly, we have y is equals to 0. Well, y is equals to 0 is the x-axis. So when we do this, we quickly notice that the area being described here, that is between, captured by those margins, it has to be this area here. So they want us to get the moment of inertia after rotating this area. So how do we get the moment of inertia? As a result of rotating that area. So again, completely up to us how we want to look at it. All we know is that moment of inertia about the x-axis will be the integral. For the x, the radius is in terms of y squared, and then dA. And then for the y, moment of inertia about the y, again, we have x here squared, then we have dA. So now I want to see which one favors either approach. Let me go for moment of inertia about the x-axis first. So if I'm going for the moment of inertia about the x-axis, the radius is in terms of the y. So if I pick a vertical section, can I make it work? With a vertical section, notice that the dimension for the radius y is going to be very weird. It's going to be different for every piece, for every point on that section. The dimension y will be different. So that is not going to be suitable here. Instead, a better option here is to pick, okay, so when we pick, the problem with, again, when I pick a horizontal section, what we're saying is that we have that upper part where things are going to change. Okay, so when I pick a horizontal section, now I see that the values of y across this horizontal section, they're going to be the same. They're going to be constant. But the only challenge we're now having is when we reach this point here, the leftmost boundary changes. It stops being one thing here. So if we're going to work it out from in this case, as in with the horizontal section, we have to be comfortable with switching the boundary at that point. What do I mean? I have to look at the problem in two parts. First, when the values of y are changing from 0 to whatever this value of y here is. So let's say this is going to be a, and then I'll take the value of, so this is going to be b here, and then finally it all ends when y is equals to this value c. So overall, when I'm integrating here, notice that when I choose a horizontal section, what am I leading myself into? Let me start with dA. How would dA look like? The thickness here will be in terms of y, so this will be a dy. The length here, it will be the leftmost subtracted from the rightmost boundary. So this is what I was saying. When you are below this line, the rightmost is x is equals to 4. The leftmost is x is equals to 1. But as long as once you exceed or you go above this, the rightmost is still x is equals to 4. But the leftmost is now being controlled by the curve there. So this is where you just have to be flexible with that part. So either way, I'll say the length will be the rightmost, I'll call the rightmost as f of x, minus the leftmost, we'll label it as g of x. The thickness will remain dy, so that the area, the dA there, will be f of x minus g of x multiplying dy. Okay, I'm writing f of x, and these must be functions of y since my thickness is in terms of y. So I don't want to present them as functions of x. We're going to present these as functions of y. Since our thickness is in terms, our d there is a dy, not a dx. With that done, when we bring it here, we're going to have this. This will remain y squared. And here, remember, I am still generalizing it and going with f of y minus g of y, and then dy here. Now, let me sort it out to say what is happening here. So we're going to split it because the leftmost changes when we reach point B. So look at it as, for the first part, we'll do as we change from, since this is in terms of dy, the limits of integration will be the smallest value of y to the maximum value of y. So we'll start from when y is equals to a. And then the swap occurs when y is equals to b. So I'll go up to b first. You see, when we're going only up to b, the radius is still just y squared. The rightmost boundary will be x is equals to 4. So this will be 4 here. The leftmost boundary will be x is equals to 1. It will be that boundary there. So here I'll have a 1 here. And then dy. This is what I'll have. But I have to combine this. So I'll say plus. Now we'll integrate. Where are we starting from? We are starting from this point now, going upwards. So now we're starting from y is equals to b, and then we're going all the way up to the final point, which is at y is equals to c. Notice that I'm just taking advantage of integration here really. So this is how we'll do it. The radius here will still be y squared, or y and then just being squared there. But for this case, what will be our f of y? F of y is the rightmost boundary. And notice that the rightmost still remains x is equals to 4. So we'll still have 4 here, minus the leftmost boundary. For once we exceed b, the leftmost boundary will now be governed by this curve. And remember, I'm saying that I'm presenting these as values of x, since I want them to be functions of y. So I need to make x the subject of the formula here. And of course, this would reduce to x is equals to y squared when I square both sides for that expression. So in other words, where there is g of x, the leftmost function, it's x is equals to y squared. So here I'll put y squared and then dy. So this is what I have to integrate. The only thing now I need to know is what is b, what is a, what is c. And to know what they are, it's easy. For this curve, at this point, what will be the value of y? The curve is y is equals to root x. At this point, x is 1, meaning that y will be equals to root 1. This will be equals to 1. There we have it. B is equals to 1. A is literally along the x-axis, so A is obviously 0. Just in B is 1. How about C? C occurs here. The value of x here is 4. So again, I'll go to the curve. Y is equals to root x. But when x is 4, this is now root 4, and this becomes a 2. So obviously, this reduces to C is equals to 2, meaning that now our limits of integration, this is going to be from y is equals to 0 to y is equals to 1 at B. This is still B here, so I'll put 1 here. And then C there, C goes to 2. And then this is done. Now we can integrate, distribute. Of course, this is just going to be 3 there. 3 can come out. When we integrate here, y to the power 2, so that is going to be y to the power 3. 3 will divide with this one here, so that you have this here. And then this is from 0 to 1. Plus, do the same thing here. Of course, here first to distribute 4y to the power 2 minus, that would be y to the power 4 dy from 1 to 2. So that this is y to the power 3. Of course, when we put 1 where there's y, when we put 0, it will just be 0. But when we put 1, this will reduce to just 1. Then plus, this side when we integrate, y to the power 2 becomes y to the power 3. So it will be 4 over 3 y to the power 3 minus, when we do the same thing there, this will be y to the power 5 over 5. This is from 1 to 2. So this is now 1 plus. When you put the upper limit, this will be 4 over 3, 2 to the power 3, that will be 8, minus 2 to the power 5, that is going to be 32 over 5, and then minus the lower limit now. The lower limit will still have just 4 over 3 minus 1 over 5. So this is what we'll have to simplify. And when you simplify this, what were the dimensions? Were we given what these were? Let's check in our problem. Did we have any units anywhere? Did we have anything? So no units were indicated here, anywhere there. So our conclusion, since we know moment of inertia has units, so once you simplify this to get a value, you're going to just give it the units to the power 4. So of course, you can simplify that separately. To get the moment of inertia now about the y-axis, I'll start that one for you, and then you're going to finish it up. So again, in this case, choosing a horizontal section will be, it will not be conducive. A horizontal section in this case will not be ideal. You'd have to use the parallel axis theorem from CEE. Oh, sorry, not that. Okay, so this is what we have. So the best thing about the y-axis is that now we don't have a change in the boundaries. So what we'll do is we're going to pick a vertical section this time. So we are coming from a horizontal, we'll pick a vertical section. The best thing with the vertical section is that for the moment about the y, moment of inertia about the y, we have the integral. The radius now is in terms of x squared and then dA. So here, the radius, which is from the x-axis, the y-axis I mean, up to where this is, notice that the value of x here will be, it will be the same expression, even if you move it vertically along on that selected section. So this is why a vertical section is better. But what does it imply? What is going to be our dA? So our dA in this case, thickness is in terms of dx. maximum minus initial. The topmost point, again, this is in terms of, these are values of y, maximum value of y. The upper part, that expression was given by what? Y is equals to root x. So the length here will be y is equals to root x, so it will be root x minus the bottom most function. The bottommost function will be 0. So this is what you're going to have there. So to get dA, you're going to multiply the length, which is just root x, multiplying the thickness, which is dx. So moment of inertia about the y will be the area integral of x squared multiplying root x and then dx. What will be the limit? Since this is dx, it's the smallest value of x to the maximum value of x. Smallest value of x is 1, maximum is 4, so this will be from 1 to 4. This is more straightforward. We see that since you're multiplying x and x to the power 2 and x to the power half, so you have 2 and x to the power half. Again, just add the powers. So when you add the powers, this will be 2 plus half. So it will be 4, 5 over 2. So you're going to have the integral from 1 to 4 of x to the power 5 over 2 dx. So of course, once you integrate this, we saw an integration earlier. So just add 1. I think that this is the one that reduces to 7 over 2. So you're going to have x to the power 7 over 2 divided by 7 over 2. And then from 1 to 4. And then when you substitute, this will be 2 when the 2 goes up. And then this will be 4 to the power 7 over 2 minus, so I'll just do this, minus. Now when I substitute the lower limit, it will just be 1. So when I substitute the upper limit to be 4 to the power 7 over 2, when I substitute the lower, it will just be 1. So whatever this, it will be units to the power 4. Okay, so this is basically how you approach it. This is how you'd work it out.